Uh, Hi everyone. It's a pleasure to be here to present you the work we did last year with Anna Zukova, Samuel Alizon, and Laurent Jacob. So we decided to try to infer epidemiological parameters directly from the genomic data. So it's linked with the previous source, but I would just explain rapidly why what I mean by epidemiological parameters. So of course, because of COVID-19, you know about the announced, and it's really linked to the how many people you infect while you are infected by a virus, and there is already some ways to estimate it. So one way is to look at the incidence through time, and it gives you a curve, and you can try to find the not from this. And there are already some models that is really fitted for this for the early outbreak, because it models are really good the exponential growth at the early stage of an outbreak. And for now, we are interested it's just a above model with sampling, a really easy one, but we want to estimate the R naught in this model and duration of infection according to this model. So when there is an infection, we also have sequencing the genome through time. So we have sequences of the same genome at in different individuals at different times. And with that, we can reconstruct the phylogeny, and we can try to find the transmission chain. But so we have really a link between sequence data and the phylogenies, and also with population dynamics. But the main question is, can we just suppress the phylogenies? And one way is we already know how to simulate data from genomic data from a model, and we want to make the backward thing, and without having to compute phylogenies. So we just have MSA. I know that we need to compute sometimes the phylogenies for finding how to align, but we assume we have an MSA, and we want to find directly the population dynamics model, the parameters of the population dynamics model. There is already some work that do it. So we can just cite BEAST because they're doing posterior distribution estimation by using the likelihood of the model. So what we can already see that is when we have a likelihood, we can compute first the likelihood of pathogenic evolution and the transmission independently. So we can't really separate have models where transmission is also linked to evolution, and it's a caveat. And also that because it runs MCMC, it's really long and very time consuming. So because the range of models is limited, there is also likelihood-free approaches which are based on simulation. So there is also some work that deals with sequence data. They reconstruct the phylogeny and then try to find the best parameters with regression ABC, or we can use a phylodip just like before, but we have to reconstruct the phylogeny. What we want to do is to avoid this and use more information, because doing phylogeny, we can maybe lose information. So we present Teddy. So thanks to Laurent for this logo made on a stable diffusion. And what we do is just like everyone have done until now for this conference, is to generate our data sets from a model we already know. And we use this data set where we know the parameters and the data, and we'll try to infer the parameter. And once it's trained, we just can use it from real data and try to infer according to this model. What we can just want to say is what should be f sigma, or function that infers, and it must follow some invariance, because when we just reorder the sequences, We just don't want it to make it depend on the nodes. And in what we follow, we also suppose that there is evolution that is independent between sites. So we don't have co-evolution, we don't have selection for now. But so we can also swap the grants, so the sites, and should not change the parameters estimates. So one solution to do it is to use self-attention. I won't go really in depth in self-attention, but our general framework is just we have an MSA where we have the sequences and a date there in the name of the sequence. We embed it in a tensor. So we have this blue square has 128 dimension of depth, and it represents, for example, an alanine, and they just removed all the constant columns. So when we don't have any imagination through all the MSA, we just discard this site. Then we transform it to give another embedding with exactly the same size, and we try to pull one data and then do a prediction through just an MLP or fully connected connecting the layer. So just briefly, the attention is done in 2 times. So we have an attention across the sequence, within a sequence. So we share information just within a sequence. So after a pass, if we look at one embedding, it contains information about the others, its neighbors within the sequence. So for example, as I said, the alanine know now how many other amino acids there is in the sequence, and also the sampling dates. After that, we also do an attention along across all the sequences, but at the same site. So now, after this attention, it's no information about the mutation through in the process. So we can say that just in 2 steps in 3 steps of attention, so site level, sequence level, and then site level, each feature has information on all the MSA. So that's why we can just pull one feature at the end and do prediction. So the main thing now is that our prediction is also it's not true. I mean, we predict an estimate and a credible interval for this estimate, just because BIST is doing like a posterior distribution. If they gave uncertainty about the estimates, and we can do it in machine learning. So that's just we have to find a good loss function to do it. So I just remember pretty fastly that if we use L2 loss, we are trying to find the mean of a certain distribution. When we use an N1 loss, we try to find the median, but we can do it with quantiles. We can just try to find a good loss. So I didn't write the good expression, but we just have a quantile that, for example, 2.5% and 97.5%, and we converge it. I know that if we train our model enough, our results will converge to the quantiles of a distribution. So we exactly do it with posterior distribution, the parameter theta according to MSA. So theta is the R naught and the duration of infection. However, we know that we don't have samples of this distribution, but it's just machine learning, so we can learn from everywhere, even if we don't have the samples. So for training our model, we just did it on the birthday sampling model, where we first have to generate phylogenies. So just for simulation, but we do it with, for example, a prior on the R naught and a prior on the duration in fiction. And then we also can generate sequences along this this MSA, this tree. And we did it 2,000 times, 200,000 times to and train on these datasets. And we wanted to test it, of course, and we compared it to BEAST on a test set that is really similar to this. Just so we use way less MSA to test, just 200 because BEAST is really long to compute. So I didn't want to spend too much time to make the difference. So we see that we can compare the R naught of predicted by BEAST. So when I say R naught predicted, it's just the median predicted. And we also can compare the statistics. So we try to find the proportion of data with the true data is in our predicted quantiles. And just it's perfect. We just find 95%, so it's really good. But we see that the relative error is quite huge because it's like 20% of error. But when we compare it to BEAST, it's almost the same. And moreover, we can just compare point by point what BEAST say and what the TEDI says. And we see that they're really correlated. So finally, we just from this, these two are the median predicted, and these are the lower bound and upper bounds predicted for BEAST and for TEDI. And we see that, in fact, machine learning is just doing a Bayesian thing without having to give him the likelihood. We just had to simulate, and moreover, for inference, we are really faster. So I know that we can't really compare it because we have the training time, but if in the context of surveillance, it might be really useful because we have just want to compute fast when we have new data. So it might be a really good thing to have this kind of model. We also say that what happens when we are out of, we don't give the good model. So I generated new data with a random R naught and a duration between 5 and 10, and duration between 1 and 3. And I remember that the prior was between 1 and 5 and duration between 0.1 and 1. And what we see is it does not give a value between 5 and 10. It just still gives the values between 1 and 5 for R naught. But when we give to BEAST exactly the same information, so we say that our prior was between 1 and 5, it still gives exactly the same. So even during on data that has not been seen during training, it will still give the same as a likelihood based method. So we can just say that the problem of model misspecification is not inherent to machine learning, it's just a problem for inference. So also we train all our model now just on 50 sequence. So it's true. We thought that because we were using self-attention, the number of sequences would self-attention is or transformers learn context between how to compare two things. So it should not matter on how long the sequences are. Sadly, it does depend a lot. So we see that so we train on 50 sequences, and we see that around we are near BEAST results, but when we have less sequences, it's really worse, especially on the duration. But what we can do is just to train on different sequences in the same time. So I just use it. So I used the previous trained TEDI, and I did inference. I did a retraining of 50,000 sequences where the length were depending. So on between 20 and 100 sequences. And now we see that just one model can also fit be comparable to BEAST on every data. Last thing to do is to compare on real data. So what we used was the 50 first sequences of data of COVID-19 genome that has been sampled in China. And we see that this time we don't give the same outputs. So it was a bit disturbing because previously we argued that it was real as beast. But what we can see is that the amino acid frequencies in this MSA of COVID-19 was really not as the same as what Teddy has seen during the training. So what we could do is just to use the same phylogenies as before, but now we use the root sequence as a root sequence for the evolution of along the tree. We use a COVID-19 sequence, and after that, when we retrain Teddy on this, or we just can fine-tune it, we did it, and it just gives exactly the same results as Beast. So to end on this, we can do phylogeny without phylogenies. Phylodynamic without phylogenies. The main thing in this work is that we don't have to reconstruct a phylogeny, and it's really great to have more models, more interesting models. This model is really beginning, but we can do really more interesting models. And we see that we are just doing with machine learning really inference-based the likelihood-based method without giving it the likelihood. And for future work, we would like to maybe to find exactly the prior distribution, the posterior distribution. So until now, we just give quantiles. This gives more information, and we could also train data on the more realistic models. So really great. Previous results were great to forward this work. Thank you very much for it.